All right. Hello, everyone. So today is our review day. I have posted the PowerPoint slides that we're going to go through. They're on the thing. I'm going to post this. Oh, thank you. Yeah. Oh, I'm so close. This is not a good idea. Hold my Anyway, we're going to go through those review slides. There's a couple edits I made to them because I made this review yesterday. It's mostly solid. There's a couple of things where I'm like, I should have put this a little differently, and I'll tell you what that is. Nothing huge, nothing crazy. You probably wouldn't think anything of it unless I said it. But yeah, this review is going to take a little bit, and in a good way. So I had my lecture class this morning. I went and I just solved through so in that class, I just have to kind of solve them through. I can't really give any time for people to solve stuff because I have half the amount of time. With that in mind, with me kind of going through this and answering questions, throughout, I only got to the capacitor slide. So, and that took an hour, 15 minutes. So all that to say, we will spend some time here. Feel free to come and go as you please because there's no clicker questions or anything. But this should provide a fairly decent overview of what's going to be on the test. That's the reason for this. As I mentioned several times, this is not sufficient on its own. And so my hope is that maybe this highlights areas that you do want to keep working on. Or you look through this whole thing and great, I know how to do this, then you're good to go. If everything I do in here, you're able to do, that's a really good sign. If there's any problem that we're working on, you're like, oh my gosh, what's going on? I don't understand any of this. Those are the ones you want to find more practice ones too. I have made your all's test. It is in as much finalized form as I think it's going to be. I'll start printing them tomorrow. And to that end, it's going to be 25 multiple choice, the 3 free response, pick 2 out of them. Each one has a part A and a part B. The multiple choice, in my opinion, and I passed them on to your TA in LA so they can also have them chime in. Multiple choice is fairly straightforward. It's very much, can you use the equations? Very generic. There's no integration in the multiple choice. There's no, there's no super complicated. It's all fairly straightforward stuff. That's 60% of the grade. Can you do the bare bones stuff? The free response is can you build the, I've said it a million times, can you build the integrals? No matter which one you pick, there's going to be an integral. 2 of the problems require you to be able to set up an integral. So even if you pick the third one, you still got to pick one of the ones that has you do the integration. So reminding you all, and we'll practice some of that integration today. There's only 3 integrals on this formula sheet. So those are the ones you need to be able to do. Can you do? And this formula sheet is posted. This is the formula sheet. Literally copy and paste it on your test. It's the exact same one. There's one integration. That's the electric field due to a charge distribution. There is the energy, the work. It's the negative of the work done, QE.S. And then there's a change in voltage. And we're going to practice one of those today because that's probably the one we practice the least. So we're going to do one today. I mentioned at the end of last class about setting up this integral for electric field to voltage. And yeah, otherwise, if you have multiple forces, can you add them together? That kind of thing. So it's going to be great. Yeah, so the free response will do you know the process? That's what the free response is testing. Can you do a process where you have to build the equations? It's not just take one of these equations, put stuff in, hit enter, and call it good. That's the multiple choice for the most part. Mixed in with do you understand the concepts? That's also sprinkled into the multiple choice. But the free response is can you build these kind of problems? If it's a net force problem, net force in the X, net force in the Y, equals MA, all that good stuff. If it's Coulomb's law, can you build the integral or voltage? Can you do Gauss's law when maybe there's a few things going on? Yeah, so we'll practice all that stuff today. That's the point. But just be prepared for that. I don't want you to have sticker shock where basically you're going through multiple choice. You're like, this is so straightforward. And then you get to the free response. You're like, this is more complicated. It is. Just be prepared for that. And that's why I try to highlight to you all exactly what stuff you need to know. And if you know those processes, you'll be fine. Yeah, great question. Hopefully, should be. It does have if you're like, that's a lot of equations. It is in the order we've learned things. And so we have learned things up until this resistance thing down here. So yeah, there's a lot more on here. That's going to be the stuff for test 2. And then test 3 will be like a little bit of optics stuff. So I say it should be. There's a chance I might need to update it a little bit more as I kind of go through it and realize what things. But if I do anything, I'll either add to it. I won't take away from it. So, anywho, all right. So, joke. Did you all? Yeah. Tyler's got that one today.
The joke of the day. Have you heard about the restaurant called Karma? There's no menu. You get what you deserve.
Nice.
Thank you. Thank you.
All right. Angelina, Tyler, do you all have any input on the tests beyond what I've said? Just as third parties that aren't me?
I would just say that if you feel comfortable, just that if you feel comfortable about the problem set, you'll feel comfortable on the exam.
And doing the same problem twice never hurt anyone. If it was hard the first time, do it a second time. It helps.
Very true.
Yeah. So your hard work will bear fruit. Like, it's not wasted time. So, yeah, great. I think I already mentioned this. Oh, no, I haven't mentioned this yet. I also posted the iClicker questions in one big PowerPoint just to make that easier. So the rule of thumb is that the raw material I give you all to practice is the problem sets and the clicker questions. That kind of forms my basis for what you all need to know. Clicker questions are like conceptual mixed with like really simple problems. Problem sets are the more involved, maybe a few more steps. That forms my basis that I pull from. The quizzes are then kind of like mini exams in their own way. They sample from those things. They sample from that. That's how I generate the quizzes, is I look at what I've had you practice and I make problems that are using the same skills and stuff like that. And so then the test should basically look like a conglomeration of your quizzes, with the caveat that your quizzes didn't have free response. So the multiple choices were a bit more difficult than they're going to be on the exam. So keep that in mind. Multiple choice is going to be fairly straightforward. Nothing is crazy in it, but it will test your like basic knowledge of things. And then the free response tests your complex knowledge. Can you do the complex processes we've been practicing? All right. So, great. There's all that. Formula sheets on the exam. The other question I get is about that note card. Yes, you can write in the front and back. I've gotten that question quite a few times, so I'll make it explicit. The note card you can write on the front and back. Do I have any note cards? The answer would have been yes, but I accidentally took them out of my backpack. You can either stop by my office tomorrow, or honestly, if you just cut a sheet of paper to 5 inches by 8 inches, I'm going to be able to tell whether or not it's the right size. The note card is 5 inches by 8 inches. If you cut a sheet of paper in half, you're basically at 5 inches by 8 inches. The note card will not save you, but it will remind you of things that you might have forgotten. So that's the reason I give the note card. It's to reduce test anxiety more than anything. But if you have not practiced the processes, good luck trying to learn them during the test. It will not go well. So anywho, it's going to go great, y'all. Look, if you've done the things, you're going to be fine. That is the rule I can basically give you all. That is the experience of students that have been in my class up to this point. If you have been practicing, you're going to be fine. If you haven't been, you're running out of time. But if you have been, you'll be fine. All right, so we're going to have like summary slides and like the main things, and then we'll have random practice problems after them. That's kind of the string of today. So first thing we covered 5 weeks ago or so. We learned about charges. Benjamin Franklin discovered that there's 2 different types, protons and electrons. Protons are positive, electrons are negative, same charge but opposite. We did the experiment with it. It kind of worked. You get net charge by doing, what do you have extra of? That's basically it. What do you have extra of? Multiply by 1.6 times 10 to the minus 19. 5 extra protons, 5 times 1.6 times 10 to the minus 19. 5 extra electrons, -5, because it's electrons. Opposites attract, like charges repel. And then we got Coulomb's law, which says if you got 2 charges, they experience a force based on K, Q1, Q2 over R squared. K is 99. Q1, Q2 have two charges, R is the distance between them. If you have multiple going on and you want to combine them, you got to break into X and Y components. Great. Let's try it. This problem does not have nearly enough variables. So look, the test problems will be written much nicer than the problems I'm giving you today. These were kind of cobbled together just to give you some quick practice. The test problems, I spent a long time making that test to make it as clear as possible so that you have everything you need and all that jazz. So if you're looking at these problems, they're not like one-to-one. These are just quickly kind of thrown together. So I got 3 charges here. Let's say these ones are a distance. It's going to be a funky distance. That one's A. That one's D. Whatever. It's fine. We're making up stuff. Draw all the forces acting on the top positive charge. And then after you do that, how would you solve for net force? This is really just testing, do you know the process? How would you solve for net acceleration? And then the last question is, if there was no gravity, what would be the direction of the net force? I had to remove gravity and for that last part. And kudos if you can figure out why part C is not possible if I include gravity, specifically given the information I've given you. Why wouldn't you be able to solve it? That's a fun extra kind of bonus thing, given the very limited information I've given you. Try it out. Yeah. For part B, it's how would you solve for net force on the top charge? To clarify that, how would you solve for the net force on the top charge? And it's more, do you know the process? That's what this is testing. Feel free to chat with each other too. The test itself, so you will work together. It's not actually directly. For part A, if you don't have 3 arrows, you did something wrong. And also remember, notation-wise, when we do forces, draw the forces starting from the middle of the place you care about. That's just a good notation. Oh, yeah. Part B. Like that.
Oh, really?
Yeah. The original picture didn't have distances or things like that.
Yeah.
It's more so just what is the so force things.
Yeah. And then you just have the S components, the Y components.
Yeah. That's more.
Is that a P?
Yeah, which I just made up now, just to like.
Okay.
But this is just, hey, what would you do
Okay.
if you did know these things? Do you even know what information you would need? So yeah, if you wanna.
I think she's actually.
Oh yeah. Angelina, you ready? Did you do at least part A?
Okay. I think I'm
So
stuck.
is it part A? Or B part A?
It's not necessary. I'm not
Is
actually
B part
having
A?
a summary. This is just you know what you would do.
Oh, so that would be
Draw all the forces
Just
is
the
part
general
A.
sense of, oh, if I'm gonna break it, if I'm gonna, so you got your arrows there. How do I put those vectors to actually
break them up.
And you know that that's an area.
Yeah.
Yeah. I didn't give you nearly the numeration of this actually do anything with it. But you know what the next step would be, why. Yeah.
All right, let's talk about the very first part, which is, so draw all the forces acting on the top positive charge. So we've got our positive charge, and I'll call this A. I'll call this, actually, maybe I shouldn't use A. I'll call it 1.
That's capital A, it's fine.
Sorry about that. All right, that's number 1, that's number 2, and that's number 3. All right, so number 1 is a positive charge, and so is number 2. And we know that positive and positive repel each other, so number 1 is going to be moved away. So that's F1. And then we have charge 3, which is negative, and we know that positive and negative attract each other, so we're going to have a force pulling it down, and that's F. Sorry. That one, the first one was F2 because it's from charge 2. I want to name them by like what particle is causing the charge. And in that case, this is F3. And finally, this is taking place on Earth, and so it's experiencing gravity. It always points down on Earth. So that's Fg. So you know it's gravity. Any questions about that? All right. Should we
Cool.
take a minute for the next part?
Yeah, well, so what I want to point out here, and this is actually going to relate to part 3. So whenever we draw these arrows, the size of them matters. That is important. So Angelina did this. Notice that F2 is bigger than F3. Why? It's closer. That matters. Don't forget that that matters. Now, one caveat to all this is the F gravity. We have no clue how big the force of gravity should be in this problem. That is something, that's why part C, it says if there wasn't gravity, what would be the direction of the net force? You couldn't actually get that answer correct because I don't give you nearly enough information to figure it out. You'd have to know the mass to know whether or not that force of gravity is a big arrow or a small arrow, because it's a completely different force that is independent of this electric force. So that's just a little caveat to this whole thing. But yeah, just to kind of, I guess, run through the rest real quick, because it's fairly quick. How do you find the net force? I got vectors. How do you add vectors together? What do we have to do? Components. You got to get the x and y. So we're going to do that. X component. What's the only force acting in the x direction? Charge 2. Where did my pen go?
It's on there.
Oh, it's stuck to the side. Yeah. So yeah, charge 2 is the only one experiencing a force. So like if we sum up the forces in the x direction, we just get the x component of force 2. That's it. Yay. If we wanted the y one, we would sum up, and that one is a positive due to y, a negative due to gravity, and a negative due to force 3. I don't need to break force 3 and gravity into its components. Why? Because they're already straight down. Easy peasy. So this is really, part B is honestly, do you remember physics 1? Part B is just physics 1. And then if I wanted to find the net force, what would I do to the x and y component? How do I bring them together? You sum the squares and you square root it. Pythagorean's theorem. Now, something I put in here on purpose, how would you find the acceleration? Who remembers our physics 1? Yeah. F equals ma. Probably one of the most important, in my opinion, tied for like one of the most important equations in physics 1. This is an incredibly important equation that describes all acceleration. Like, It's fundamental to the universe. It's great. So yeah, you want the acceleration through the magic of just divide by the mass of it. You would need to know the mass of this object, which you would need to find the force of gravity anyway. And the last one, if I wanted to find the direction of the net force, I'm going to draw F2. Then I'm going to draw F3. It's a little bit smaller, and we get roughly something like this. We can't do it with gravity because who knows how big gravity is, and that would change things drastically. But this, you should be able to get a sense of it. It should roughly be kind of up to the right. Roughly. There's some wiggle room here. Cool. There you go. Do you know these things? That's the whole point of this. Fundamentals for charge forces. Yay. Cool. On to fields. What causes these forces? We made up something called a field. Charges make these fields everywhere. You put a charge in said field, boom, you got a force. Just like gravity. The Earth makes a field everywhere. You put an object with mass in it, boom, it experiences a gravitational force. Defined by the force divided by the charge in it. Charges make these fields. So one makes a field, the other experiences a field. So kq over r squared, and you can add them all together. So if you have multiple, just like we can add forces, we can add fields. If you have an infinite amount of them, you got to integrate or do Coulomb or do Gauss's law. Those are kind of the two options. And inside a conductor, the electric field is zero. That is a fact that you all need to know, and it's so important. It shows up on 2 of the slides. Wow.
For kq over r squared, that q is the charge making the field, right?
Yeah, great question. This kq over r squared, this is the q making the field. So if I call this E1, it would be Q1. Yep. One makes the field, one experiences the field. So for example, up here, if I had one charge making the field, then this would be the force of 1 on 2, and charge 2 would be the one experiencing the field. I know it's easy to get those things kind of mixed up, but just think through what you're doing and why you're doing it. That's that conceptual understanding. These equations are sentences that mean something. If you can only say the sentence, but you don't understand what it means, it's kind of like reading an English sentence, but you have no idea what you're reading. You can sound out the letters, but you have no idea what the meaning is behind it. When you understand the meaning behind it, that's when you can start doing cool stuff with it. That's when you can start making your own sentences and stuff like that, as silly as it sounds. All right, cool. Same situation, but now find the field at the top. And hypothetically, if the bottom charge was experiencing a field to the left, we don't say why, we just say hypothetically if it was, which way would that charge want to move due to this field to the left? So that's kind of like a separate question. It's not supposed to be a trick question, it's very straightforward. So yeah, find the field at the top, and then hypothetically, hey, negative charge sees a field to the left for some reason. Which way will it move? Sees a net field to the left.
Right. Yeah. Technically inside the church. Yeah. Yeah. So if there was a negative.
I guess it's just asking for the top.
Yeah, that's what I was just thinking. Right. Yeah.
Right.
Because
I feel like they also gotta be like, they kind of probably show it like this, right? Like since they're both positive.
But I think like because what's the direction
Like electric field pointing that way.
All right, so this question is
Oh, so it's
basically,
just
I mean, it
field.
ends up being very similar to the last one. We got 3 charges, uno, dos, tres. We want to find the field at the top. The field due to charge 1. I put this in the last slide, but I don't know if well, maybe I didn't put it. Oh, I did. Electric field lines point away from positive and towards negative. So we draw our fields. The field due to 1 points away. It's a certain size. The field due to 2 points towards it. It's smaller because it's farther away. Field due to 3 doesn't exist because you can't make a field where you're located because then you'd be affecting yourself, and that's weird. Doesn't happen. So net field, boom, you got 1 up, 1 down. The net field is somewhere in between. If, hypothetically, there was a field on the bottom to the left, why? Who cares? It doesn't say why. It just says there is. Which way would that negative charge want to move? Rule of thumb. Electrons always do the opposite of what you intuitively would expect. So, intuitively, you think it'd go in the direction of the field, but it's negative, so it goes the other way. Boom. Forces to the right. Which way is it going to move? To the right. Why? There's a force to the right. Why? Because fields are defined in the direction a positive charge would move, so negatives do the opposite. Negatives always do the opposite of what a positive charge will move. This will also be true when we get to magnetic fields. They always do the opposite of what a positive charge does. That's what makes them different, special. Cool. All right. This PowerPoint slide is already, this is not a new slide. I copy and pasted it from a previous PowerPoint. How do you set up a Coulomb's law problem? Draw a picture. Very, very important. Draw your charge distribution. Draw where you're finding the field. Label the distance, and we'll label this R thing you'll see. Write dq as charge density times dl. Every problem I'm going to give you with this is going to be a 1D charge distribution. Why? Because I can't have you do double or triple integrals because you're learning them now. So you're spared. So we're only going to be working with 1D charge distributions. You're going to use this integral if you have either a finite line of charge or a line of charge with a non-uniform charge density. The 2 reasons you're going to use Coulomb's law is either you have a piece of a wire, a loop of a wire, or a non-uniform charge density. Gauss's law is for everything else. Gauss's law is for everything else. All right, so great. Write dl in terms of the spatial coordinates. If left, right, dx makes sense. Up, down, dy makes sense. If a circular loop, use arc length. Break into x and y components. How do you do that? Draw an angle, do normal vector stuff, and then get everything in terms of known variables. Yeah, so you're going to use this. In fact, actually, let's look at the Gauss's law one to see. Basically, you're going to use it. When do you use Gauss's law? Infinite rod or line with uniform charge density, infinite plane with uniform charge density, or spheres. So basically, if you have something that's either finite, Coulomb's law will come when either it's a finite rod or line, or it's a rod or line with a non-uniform charge density. You're not going to use Coulomb's law for a plane or for a sphere or for a cylinder because good luck, have fun. It'd be very unpleasant. So, all right. So this problem, this is a little bit more, this is going to be more complex than what I'd give on the test. But if you understand the process, the process is straightforward. So I'll say this answer is going to look a little uglier than one I might give on a test, but this process, if you can do the process, all these are basically the same difficulty, honestly, as weird as that sounds. First step, draw a picture. I got a rod on the x-axis with one end at the origin, the other at x equals infinity. It has a charge distribution of lambda equals e to the x. My question is build the integrals to find the electric field at some point located at x equals negative a and y equals b. So first step, go through these steps. These steps walk you exactly through how to do this, but your success is very much going to depend upon how good your picture is. So draw that picture first, draw your charge distribution, identify where you're finding the electric field, and then the extra piece I might add to that is pick a little DQ, pick a little piece of the charge and draw what the field would look like in variables and all that kind of jazz. If you can't draw it, everything else is going to be terrible. And one thing you're going to want is a coordinate axis. This is a fun one.
Yeah, so the field would be somewhere here. It's at 1 point. Oh, I see what you're saying. Okay.
To clarify, just one. We're just trying to find the field at 1 point. So that coordinate is negative a comma b, is where we're finding the field at. Oh, the answer to this? Oh, the answer is disgusting. No, it's got an exponential in it. We don't worry. I did not make these. Making solvable integrals really hard. No, it's still like I'm not sure. Absolutely exists.
This has changed now that it's
Original is hard.
I was just looking at the triangle with respect to the point.
So so here's the first step. Draw your coordinate axis with your origin on it. That's going to be important. Where does my rod start at? At the origin. So I start my rod here, and then how long, where do I draw the rest of the rod? I just make a line that goes infinitely to the right. Woo! I can't draw it infinitely long, so that's good enough. That's my rod of charge. Great. Next question, where am I finding the field at? Draw a dot on this picture at the location where I want to find the field. So you need to know what your charge distribution looks like, and you need to know where you find it. I mean, it makes sense, hopefully, that those two pieces of information would be useful. All right, where do I put my dot? Yeah, the second quadrant, off to the left, and then do I go up or down? Up, great. Some arbitrary point here where my distance is A. It's negative, so it's off in that quadrant, but, it's just some distance A. And some height B. That's, what am I finding at this point? It's always good to have your mind on the objective. What's the end goal? Find the electric field at this point. This line of charge makes a field everywhere. I only care about at this point. And if I give you a problem like this, I'm going to say find the field, nail the integral at some point. And I'll tell you where that point is located. Cool. All right, the next step. And I maybe should have put this in my steps, but this just helps. It's not like critical, but it really does help. Pick a tiny little DQ. Pick a random spot on that wire. I don't care where you pick. Pick a little tiny DQ and draw what the field would look like at that point due to that little DQ. Go ahead and practice that. If we can understand a piece of this, then that's going to help us understand a bunch of pieces of this. All right, so which way should that field point? Something that's going to be helpful for drawing that field is we know that fields either point towards or away. So it's really helpful to have this little dotted line to give me a nice little reference, and that's going to be useful for another reason. Question to you all, is this charge distribution positive or negative? How did you know that? E to the x is positive. How do I know what my charge is? My charge distribution, plug in a positive, e to the any positive x is a positive value. Great, it's positive charge. All right, so is it going to point away or towards? Cool. What do we call this? DE. It's a little piece of the field. It's not the whole field. It's just a little piece. Now, something that's useful, and I did mention this in my instructions, something that we know we're going to need. So if we like start to write this integral, so E equals the integral of k dq over r squared. Look, I got my dq in my picture. What other variable shows up in this equation that's probably kind of useful to show in the picture? Go ahead and label r on your picture. What is r? What does it represent? Draw it on your picture. So this comes down to, do you understand Coulomb's law? So what does r represent in words? The distance from what to what? The charge to the point. It's that little dotted line thing I drew. Great. Now that we have that in the picture, that's going to be super helpful. Trust me that it will be. I mean, trust me that it will be. All right. Go ahead and start going through the steps now. Replace dq with lambda dl. Replace dl with whatever. Reference that slide and go through the steps. Choose the bounds of your integral. Start going through it. I'll give you all some moments. Yeah, that's good. Yep. Oh, it looks terrible. It's disgusting. The final integral answer is disgusting, like as far as solvability. But that's on not having you solve the integral. Building it, though, is very regimented. Follow the steps. It's a process. How do you get good at the process? By doing it. Close. You're getting so.
I broke through the Y and X. I don't know if it has to be that.
Yeah. So this side of the triangle. So rated x. Yeah, you're seeing that data. Too big, so go ahead and make it. You run your big R. You need to make up an angle.
Yeah, I pulled it out here. I made it. But you would have to have it. So I wrote. I didn't really write it, but I went.
So you said this is
See, yeah, I did that and I just combined it because I pulled out two of them here because you have R squared equals A squared plus B squared.
no, this is technically yeah.
Just write it as 3.
So I think literally that's it.
Oh, okay.
A plus X. Yeah. You have to add the variable.
Oh, got it.
With the Y is never changed, which makes it solvable, even though it's low. So this would be
In all honesty, it's probably just
plus the trig sum.
that X plus
It's probably increased by partial maybe
I'll come around.
oh wait.
All right, so the next two steps are pretty straightforward. They're very formulaic. dq gets replaced with lambda dl because it's a line of charge. What are we going to replace dl with? dxy. My rod, we're integrating over the rod. What is my rod situated on? The x-axis. Makes sense that we're going to integrate over x so we can integrate over the whole rod. Remember, this integral is we're doing something functionally. We're figuring out how much each of these pieces on the rod does. So we're integrating across the rod. What are my bounds of this integral then? Where does my rod start? Where does my rod end? Starts at 0. It ends at infinity. We're integrating over the rod. You're integrating over all your charge. Where's your charge? Your charge starts at 0 and it ends at infinity. We're building the thing. All right, great. We did this step. Next step. Again, it's very formulaic. You just go. We're building the integral. Next step, we got to break into x and y components because this integral right now is saying that I can just add all my components no matter what, and that is not true. An integral is an infinite sum. I can't add x's and y's. I got to break it into x's. I can add those together. I can break it into the y's, add those together. So ex. Now, before I even start solving this integral, because of the way I'm teaching you all to do this by using this cosine of the angle, there is something we have to do in addition to this. Before I even start writing this integral, we should realize something. Which way does this field point? Left or right? So what do I need to put in front of it? You need to put a negative sign. Why? It points to the left, and all of it points to the left. This is the way I've taught you. It's not the most robust way by using this cosine and sine of the angle, but it's sufficient for you all. Physics majors will learn a more robust way in the future. But it's sufficient. I'm not giving you any problem or we'll have any problems with it. dx over r squared. We need to make some angle in this picture. The way we've been breaking things into components in this class, you got some random vector, you want to break it into components, you make up an angle, you do SOHCAHTOA. Same thing here. So, we need to know where to draw the angle. Hey, look, here's my vector here. It sure would be nice to know this angle. That's the vector I'm trying to break into components. Where does that angle show up in my picture? Oh, it's this angle down here. That's going to be helpful for us later on. So, given that angle, do I multiply by cosine or sine? If I want the x component and I have some vector like this with some angle like this, my x component is the adjacent side, so it's going to be cosine. Great. You have now built the thing. We can do the same for the y component. My y component, positive or negative? Because it points up. We are still integrating over dx. I know that one of the things that is easy to fall into is like, but wait, we're finding the y component. Shouldn't we integrate over y? You have to remember what your integral is doing. What are we even doing with this integral? Why are we integrating over x? We're integrating over all the charge. My charge, I don't care what x and y component, it goes left, right. That's not what the y component's doing. It's not making my rod go straight up. Anywho, what I want to then, the last step for you all is to write your variables in terms of other known variables. If there's something else that's going to be useful to add to your picture, pro tip, draw a triangle.
So the original integral is finding the magnitude of the field that
Yeah.
you break into components.
Yeah, it's a great question. The original integral is finding the magnitude, but the problem is you can't integrate as is because it's assuming you're going to be able to like add x and y, and you can't. Like we've done hopefully enough problems where you realize you can't add x and y components. You have to split it up. You can't just go straight to the magnitude. It's just not how we work with vectors. All right, so yeah, try to get these variables in terms of the ones in the problem. And the first question is, k, does k change? No. Does lambda change? Well, no, lambda is e to the x, like that. Well, is lambda a constant? Can I pull it out? It changes with respect to x. What am I integrating over? X. You cannot pull lambda out. It's a function of x. All right, r. Does r change? How do you know whether or not r changes? Just pick another piece of charge. Oh, it's farther away. R changes. Does my angle change? Yeah, how do you know that? Again, pick another random spot. Oh, my angle is different. You got to think about what these variables represent in your picture and whether or not they're changing. Like this is why this is like in the free response category. It's a process. It's do you know what you're doing? And it'd be cool if you know why, but at least you know what you're doing. Can you do this complex process? Can you do multiple steps in a row? Can you build the equation you're actually solving? That's where stuff gets cool. When you're just using canned equations, not as exciting, not as meaningful. When you can build the equation, you can do a lot more cool things. So anyway, try to do these subs. I'll walk around and help you all out. There is a variable that we use. Draw a triangle on your picture if you haven't done so. That's my hint. Let's see a triangle on your picture. That's gonna help us.
You're summing over all
Okay, so you pick the point way over
individual
here.
small slices.
Pick a point over here. Yeah. So you pick a little tiny piece of chart here. Pick one that's more. Yes. The horizontal distance
What is it-
changes.
what is
It's no
the
longer
velocity?
just A. It's now A.
Do you think it's actually the answer?
What direction?
Yeah. And now you can see it depends upon. It's not a constant. Yeah. Once you do that,
But
that'll
remember, we are measuring at a point. So if the velocity
Zero points. Yep. Yep.
It's either X over
You're adding
Y or Y over Y.
positive. Because if X was 0, it would be A.
Oh, okay. Yeah.
Does that make sense? That's just the bottom of the triangle.
Draw a triangle.
Square root. Exactly.
We know we gotta get things in terms of R. That's a hypotenuse of some triangle. Make that triangle. That's gonna reveal all the things.
You don't have quantities
That one's the height stays.
But yeah, this is the. So I'm not gonna ask this like this. It's not terrible, but
X is the variable.
It
Yes.
is very formulaic. Draw the picture. If your picture's good, everything else will fall into place. If your picture's bad, and I'll tell you all on the test. I'll actually probably give you the chart distribution. And I'll also tell you where the origin is on. Okay. But I'm not gonna show you. I may or may not show you where the point is. I think I will actually. But it's not gonna have R listed. It's not gonna have the angle drawn. Those are the things you gotta know to be able to draw. I don't know if you'll keep it.
Oh yeah, it says just build it. You know, you try to. I don't even think it converts.
If only it was X squared, Y squared, so if I draw a triangle, we have
It doesn't start this root.
Oh, you use this side of the triangle, A and B.
Oh, okay, I'll take, yeah.
You have to remember the relationship is hard.
And that's how you
Because the formula uses EQ, and if you change the dx, lambda dx is going to be E
not
dx.
much X though.
Okay.
X plus A. Boom, now you got your two sides of the triangle.
All you're doing at this point is just you're plugging in. You know that lambda is E dx. I know.
Y is
No, Y is constant.
I hope I'm not big enough for what
Yeah, and that's where the picture reveals all.
Yeah, there's no
What variable is changing, what variable is all right, so I got a triangle. How big is my left side, my vertical side of that triangle? Because if I want to find R, I should probably do the bottom squared plus the height squared. You know, triangles. Yeah, what's that? How big is this side? It's B. How big is the bottom of my triangle? My DQ is some distance X from the origin. So what's the total on the bottom? R squared. Well, I'll just write this. It's fine. R equals the square root of X plus A squared plus B squared. It's a triangle. You have this R. You're going to write in terms of the bottoms and the sides. We draw the picture. We see it all. It's lovely. Cosine of theta. What's the rule? SOHCAHTOA. Cosine of theta equals what over what? Adjacent over hypotenuse. What's my adjacent side in this picture? A plus X. What's my hypotenuse? R. Sine of theta is going to be opposite over hypotenuse. What's that one going to be? What's my opposite side? B over R. When you make the substitution, you get the integral from 0 to infinity of k you know, we can go ahead and put what lambda is. Dx over, we're going to get this x plus a squared plus b squared. And I'll be kind, we have the time for it. A plus x over another x plus a squared plus b squared to the 1/2. You add those together. I don't have enough room. The bottom turns to the 3/2. All I did was plugged in this cosine up there. And I plugged in the r. And then I ran out of room. Now, if you're looking at this and you're like, oh my gosh, this is so much work. Am I going to have to do this in a free response? So on a free response, to make this a bit more manageable, I will just ask for like one of the components. Granted, if you can do one of them, it's pretty easy to get the other one, but for the sake of time, just one of the components. Also, if I ask this kind of question, I do actually give you a picture, like I did drawn picture already. But the picture won't have r on it. It's not going to have the angle drawn on it. You have to be able to do that. And do we solve this integral? No, that's an awful integral, like gross. You're welcome to plug that into something to see how disgusting the answer will be. It will be it's very easy to make it not unsolvable, but almost probably unsolvable. It's hard to say. I have no clue. So much of math is just figuring out new ways of solving integrals. This other one, very similarly, just turns into, instead of having on the top a plus x, we have a b, and the denominator looks the same. X plus a squared plus b squared to the 3/2. But this process, do I need you to be able to solve this exact problem? I need you to know how to do the process. Can you draw the picture? Can you draw the r? Can you break it into its x and y components? Can you make those substitutions? At the heart of all this is how good is your picture, really. If you haven't seen how important this picture is in this process, it's very important. But yeah, you don't need to solve the integral. That's gross. If I have you solve an integral on a test, it'll be an integral that would have been given in your Calc 1 class. Okay? That's if I have you all solve integrals, they're going to be like Calc 1 integrals, basic integrals. No trig sub or trig identities or any of the cool tricks that you learn. No Taylor series expansions. Yeah. All right. Cool. Gauss's law. Another way to solve electric fields. Because Coulomb's law, we picked like the simplest line of charge. It's like as simple as it gets. And even then you saw the integral gets disgusting. This lets us solve crazy problems that would be otherwise impossible or very miserable to solve with Coulomb's law. Before that, remember the definition of Gauss' law comes from flux. You do need to remember what flux is. There's two definitions. The integral of E dot dA. Remember that integral of E dot dA is the same thing as writing the integral of E cos A cosine theta. If E is a constant, dA is a... I gave you all some problems where I had like a plane and I said find the flux through it. Make sure you can do those kind of things. I gave you problems where I said, hey, here's some charge. Here's some Gaussian surfaces. What's the flux through it? And it was, make sure you can do both sides of this. And then, yeah, Gauss' law is all about choosing the right Gaussian surface, drawing a good picture, solving E dot dA, and solving Q enclosed over epsilon naught. Yeah. If E is a constant to come out, integration would turn it into A. Yeah, so that's a great question. So, as far as actually using Gauss's law, remember we choose shapes such that the integral either becomes 0 or E times the area. That's why did we choose these shapes? We chose them so that either parts of the surface were 0 or parts of the surface the electric field was a constant. It's true for the following situations: infinite radar line, infinite plane, sphere. And then this is the step by, it is a formulaic process. Draw a picture with the correct Gaussian shape. Depending on what your geometry is, your area is going to vary. If it's a sphere, you're going to draw a Gaussian surface that's a sphere. So you're going to use the area of a sphere. If it's a plane, you're going to have the area of the two flat sides of the plane, the top and the bottom. If it's a cylinder, we're doing the area of the sides because the top and the bottom, the flux is 0. In the case of the flat plane, the sides of the cylinder were 0, and this only has one surface. All right, solve for Q enclosed. How do you do that? If you got all the charge or none of it, easy. If you have some of it, we're going to do that charge density trick, and we've done that before. Set the two sides equal to each other and solve for E, and I've added a line to this. I told you I'd show up again. Inside a conductor, E is 0. And when I say you're inside a conductor, I want to clarify something. This means you're in the material itself. You're in the metal. So to clarify what I mean by that, say I have the following situation. I have a hollow metal sphere. And then, so this is a metal sphere. Let's say it has charge Q, and it's metal. Then let's say I have an insulator inside, some solid insulator that also has a charge of Q. If I ask you to find the electric field at some point between the two, the electric field there is not 0. Okay? So when I say inside a conductor, I don't mean like if it's hollow, you're inside of it that way. No. What do I mean by that? I mean you are inside the conductor, in the metal itself. If you are physically in the metal, say physically, if you're in the metal, if I say find the field inside that object, that's where it's 0. Okay? And if you're like, why is the field not 0 inside? Well, do some problems and find out some things. We'll practice Gauss's law now. And the quick answer is if I drew a Gaussian surface, my Q enclosed would be Q, not 0. All right, so great. This is the process. If you have not done this process, this is going to be very confusing. If you have done it, hopefully these next ones are fairly straightforward. 3 metal wires with length L are nested inside each other as shown. The center wire has a charge of 3Q. The next one has a charge of negative 2Q. And the outermost one has a charge of 5Q. What is the electric field inside the wire with charge 2Q, negative 2Q? When I say inside, I mean in the material. And what is the electric field at some distance r outside of all the wires? So part A is that red line. Part B is this one. On the test, I tend to have these things kind of labeled so that clarity is there and all that jazz. But try it out. Try part A, try part B. Go through the steps. Draw your Gaussian surface. Yada, yada, yada. If you're in a metal, things. In fact, for part A, look, I don't want you all to go through the whole process. I don't want to waste a bunch of time on part A. What's the answer to part A? Why? Great, you're in a metal. And that's it. Don't do any math. Don't do any process. If you are in a metal, boom, you're done. E is 0 inside a metal. Inside metal. Inside conductor. Metal is a conductor. Okay? Great. Part B, you need to go through the steps. Draw your Gaussian surface. Make sure you know what you're drawing when you're doing it. I'll go around and ask questions.
You add them up in the
So I have to put L when I first did this.
Yeah. I guess that's kind of implied.
So what I'll be walking around for is seeing, are you drawing this? And are you drawing that like dotted line Gaussian object? And then I'll ask you questions if you know what shape that object actually is. I'm looking to see. That is
The area of a sphere.
Yeah, right. Or is it? Oh, for higher, right. That's
Cylinder for the planes and the line. This one you just saw another.
Great.
But that's what you. That's what you use it partial here. This is all of it.
Yeah.
You can get like. I think you get charge your shape.
It won't be clear. But I'm asking, what's the full way to do? Is Q and close?
What's your area?
Wait, we're going right here. At the find the charges.
For a cylinder.
Oh, wait.
It's a wire.
Oh yeah, because like charge your but not back.
You forgot to put L for the wire.
Basically, if you create a bigger ball,
This is a cross section of the wire. At least that's what he's doing.
yeah, create a bigger ball. And you make all of those blue things all of those fields.
No art. Actually, we'll actually double check.
Pretty sure.
So that's why the Q and close is 6.
There's no check there.
All of the fields that we have is showing all of our major
All right, beautiful.
Yeah, you're doing-
That dotted line, what is the shape of your Gaussian surface?
Two IR.
The reason I ask is because when it's a cross section, a cylinder and a sphere look the same. Right.
Oh my god. So you're just doing
That's just
the rectangle. Cylinder.
2 pi r times the.
How's it going? Alright. Oh, it's a cylinder. Why?
Oh, it's a wire. So you
2
can
pi r
do it as like
flat.
yeah.
And then multiply that by the That's what we do.
The reason I ask is it's
This is
all the problems I'm getting is spheres. All right. What is the geometry of my charge? Is it a rod, a plane, or a sphere? You have to know what your object looks like. Which of these pictures describes it? Is it a rod, a plane, or a sphere? It's a rod. They're wires. Wires are rods. So what's the Gaussian shape I'm going to draw around this? A cylinder. Now, if you're like, from a cross section, so this is what it looks like dead on. This is my cylinder. If you'd like, here's what it looks like from the side. Here's my wire from the outside. What am I drawing? I'm drawing I'm drawing the cylinder along it. If you take a cross section of this, it looks like a circle. I am making this explicit because if you don't know what shape you're drawing, you might think this is a sphere because the problems you've been doing are spheres up to this point. You got to be careful. You got to know what you're doing and why you're doing it. And so when you all set up this left side, so you're solving the integral of E dot dA equals Q enclosed over epsilon naught. This left side, you care about the area. What do we use the area? When we're doing a rod like this, what's the area going to be? 2 pi RL. It's the area of the rounded side of the cylinder. That's the strat. Equals. Now you all got to find Q enclosed. And interestingly, in this problem, that's pretty simple. But I'll let you think about it for a bit longer if you haven't gotten there yet. The final answer will be, I'll put the final answer in case you're at that stage. Okay, ignore that. Pretend like that wasn't there. Yeah, I'm so used to writing K that I just sent a default to doing it, but no K. 6. Yeah, no G's. No G's in this problem. Look at your picture and how much charge is enclosed by your Gaussian object. How much is inside of it? That's what Q enclosed represents. How much charge is inside your Gaussian object? A Gaussian surface. You got one circle. So a cylinder, inside of a cylinder is just L circles. Yeah, it's a good question. That's really the derivation.
Like in the U.S.
So
It's along up the coast, and he's still left in Virginia.
No fall.
Over in Virginia.
Where's that?
No, it's to the left of North Carolina. Obviously, West Virginia is West Virginia. I don't know why. Yeah, it makes a lot of sense. It's closer than I thought, actually. It's above Georgia. That's cool. And why is it going that way? No, it does seem like it's that way.
All right, so your Q enclosed, we got all of it. What is all of it? Just add it up. 3 plus -2 plus 6. 5 plus 5. Over epsilon naught. And through algebra, you get the answer. So this is one example of Gauss' law. I will straight up tell you on the exam, if there's a free response on Gauss' law, it's not just going to be one solid object. It's going to be a couple of objects or 3 objects like this one. Do you know how to set up the problem? Do you know how to find charge enclosed? I care about the process. I don't care about whether you found the equation for the electric field inside of a solid sphere. And you can just like regurgitate that on the test. No. I care about, can you do Gauss' law? Can you find the charge enclosed? If on your formula sheet you just have a bunch of equations for electric fields, you do a bunch of random objects, good luck predicting what object I'm going to put on the exhibit. Specifically, good luck predicting what combination of objects. Now, one caveat to that, I'm not going to give you a problem that's like a sphere and a rod. It's going to either be a bunch of like spheres inside each other or a bunch of rods inside of each other. At most, the only other thing I can do with a sphere is like, if you make a sphere infinitely small, it's a point charge. But that's fine. That doesn't change anything. Anyway. Yeah, great question. How would I word a problem where it'd be somewhere in between? So I've done this a few times. What I do here is I have to give you the radiuses of every object. So I'd say like the inner object has radius 1. The second object has an inner radius of R2 and an outer radius of R3. The outer object has an inner radius of R4 and an outer radius of R5. And then I'd say my R is less than this value and bigger than this value. I'll straight up tell you, I think on the test, I actually give the picture if there's going to be a Gauss law problem through it. Like, hopefully y'all can guess that at this point. This is not a shocking thing. I show on the picture where I want it. I actually labeled it on the picture because I don't want you to miss the problem because you misinterpreted where I wanted the field. So, cool. All right. This one is a fairly generic one, but it does get an idea of do you know what you're doing. This is not a super complex one, but we're going to use the answer to this to solve the rest of this problem. Find the electric field inside and outside of a uniformly charged sphere with net charge Q and a radius of R. This is an insulator. This is a solid sphere that is an insulator with a uniform charge spread throughout it uniformly. Draw the picture, pick some spots, pick a spot inside, pick a spot outside. It's 2 problems. Find the field. For what? Yeah. So this is multiple options. This is multiple.
I feel like I'm doing the potential.
I guess you could.
Is it the same setup though?
I think it's very
So yeah, multiple.
This one took me a while to
I didn't
figure
read
it
it.
out.
Shells, or like maybe there's a sphere in the middle, or there's a sphere on the
Mm.
outside, or maybe there's cylinder like this one.
But we won't need to do like multiple different types of connections. Like it was just a cylinder.
It's one. It'll just be a set of Gauss law once and 10. Yeah. Find the electric field at this specific spot, and that's a one setup. But it's can you draw the right Gaussian shape? Can you find the right charge enclosed? That's not testing.
Like it looks like it's all the
Wait.
Sphere? Oh, you're close. You're missing a number. The area of sphere. Four parts. Four of a three part. Yeah. So the nice thing is yeah. Instead of an R cube, go with R squared, the other three.
Right.
Or have that new card.
it says electric potential at the top, but I'm thinking
We're gonna use this answer. So this is from electric potential because the original problem is find the potential, but to find the potential we need to know the field. So yeah, so that's I really like this problem because it makes you practice Gauss laws and then do this. So I broke it into the two explicit pieces. Yeah. This is to prepare us for it's gonna show up again, but I'll say sign the voltage, and that's why these answers are all in voltage.
Oh, okay.
Yeah. If you're looking at the slides, the answers are going to show up later. This problem is for electric potential, but we have to find the field to find the potential. So if you're like, what's going on here? Why are all the answers in B? That's because that's the future thing. And that's the one that we'll have to do with the grade. It'll be great. So much fun. Great, Tyler. Never feel like people are at a decent point if you want to do this one. It's a fairly
Yeah. Is it? Am I doing it right here?
yeah, it's perfect.
And then
Yep.
this.
Capital R cubed. Yep.
And then I
That's
can
it.
just write that too.
Yeah, and then what's cool is then when you're outside, you can resolve it. And then outside is this turns into a little R cubed, basically.
Oh, because you just figured it out.
It ends up becoming a little chart. Yeah, but you'll do Gauss's law again. But in the second case,
How would I? So.
it's the same process, but now you have all the charge. You draw it.
So this is the whole chart would just be.
Yep. And then the area is still 4 pi squared.
Oh, gotcha.
But what's cool is
Big R.
Yeah, but what's cool is here you see this R cubed came from like how much of it do I have enclosed? Oh, I have all of it enclosed, so then that turns into little r.
Wait, can you say that again?
So like when you're on the surface is our we call it like the boundary. So when you're on the surface, that R turns into like capital R, and you end up with that. So you can see that they kind of connect to
Oh,
each
so
other.
okay, yeah.
Those are always-
Then you would just have R, big R squared. On the
Yeah,
bottom
it's
of the
always
bottom.
cool when you have two different regions. The interface should be true.
Yeah, I don't understand because if you're multiplying by that, right? Like, would it just become Q over R squared, big R squared?
Yeah.
And then this, when you
It ends
divide,
up.
you divide by it, don't you?
Yeah, you're doing good. That should be little r.
Oh, okay.
Because you're a Gaussian object.
Yeah. Oh, okay.
Yeah, if your picture's good, everything will make sense. Or at least more sense. If your picture stinks, good luck. And pro tip, when you're drawing your picture, draw your Gaussian shape as that dotted line. Otherwise, you might lose track of which one's which. I don't know for sure, but it's just a nice little notation thing. Draw a solid line for the physical objects, draw dotted lines for the fake thing you're drawing, that fake Gaussian surface. Helps to keep track of which one's which and whether one's on the outside and one's on the inside.
Yeah, I don't think I understand the second part.
So if we draw the picture for it, so here's our sphere.
Mm-hmm.
Have some distance out here.
Okay.
My area of that is 4 pi r squared. How much charge do I have?
Q.
Really dumb.
Oh, so I just said that. How do you get into this form?
That's voltage.
Oh,
That's
oh,
voltage.
okay. Oh, that's what was confusing me.
Yeah. Are you inside or outside? Which one are you solving? You're solving inside? Okay, so you're solving inside, and you want your Gaussian surface to be inside. There's two different,
Okay, let's just say this is outside.
Great, now we're outside. Okay? So then we do E dot dA. What is my area going to be? Is it the area of my solid object or my area of my Gaussian object?
That's
It is the Gaussian. It is the one where the field is at little r. Yep.
So it'd be little.
Yep. Because that's the surface area of the
Sorry, I
solid.
thought you were saying.
No. 4 pi little r squared. That could be the area of your Gaussian.
Yeah, I know those Q over V. How do you put Q?
And then we go to the right side. The charge is inside of my Gaussian. All of it's in there. Great. You divide it over and you're done. Now when you're inside it, we're going to pick some spot. Just pick a random spot you want to find for us.
I picked that.
Perfect. Draw a new Gaussian surface. The new dotted line. Awesome. Now we're going to do the same process. E times A is the area of the Gaussian object. Still 4 pi squared. That's E.
the big R in this case is the big R.
So
Little R is the MC.
No, it's more complicated. No, still the Gaussian object. You still use little r. Capital R is the radius of your big object. Yes. E dot dA is always the area of your Gaussian object. Always. All right, just to draw out part B. In case, okay, hopefully part A, you're like this. Outside of it's hopefully easy. Maybe not. Maybe so. I don't know. Great. Here's my object. If you're at some point here, boom, that's outside and I'm finding the field there. If I want to find the field inside it, boom, I pick that spot and I draw that one there. Why is the outside easy? Yeah, how much charge do I have? All of it. So it's really easy, times 4 pi r squared. And then I'm going to give you all a hint for the other side. So great, rearrange it, easy peasy. The inside, my hint to you all, and it's actually in the notes. It's in this, remember this process. If you have all of it or none of it, easy. Just put what you got. If a partial amount is enclosed, find the charge density. And I'm actually going to write this out for you. How is my charge distributed? There's 3 types. There is a line charge density. There is a surface charge density. And there is a volume charge density. What kind do we have in this problem? Is my charge over a line, over an area, or over a volume? Great. Y'all got that down. So this is true. It's a uniform amount. If I have the entire piece, I can take the entire charge, the entire volume, boom, get the charge density. The analogy I keep using in my office, and okay, I'll just use this wooden tabletop. If I had this wooden tabletop, how could I find its density? This wooden tabletop here. How would I find normal, good old mass density? Mass over volume. I'd rip this thing off. I'd measure its mass. I'd measure its volume, divide the two. Or I could just take a tiny piece of it. If I take a tiny piece of it and measure its mass and measure its volume and divide the two, I will still get its density, assuming it's uniform. Density is, if it's a uniform density, it's the same everywhere. It's how it's distributed. So I could take a small piece of it or a big piece of it. Why am I saying that? That means I could take the Q enclosed and the volume enclosed, and that also will give me the charge density. If they equal each other, I can solve for Q enclosed, and you end up with the ratio of volumes. You can try that. You can rearrange that for yourself. You can rearrange this equation, just this right side, to find the Q enclosed, and you'll find it's a ratio of volumes. What's the fraction of my volume I have enclosed? Multiply that by the total charge, and boom, you got it. So I'll leave you all to that. And Tyler will beautifully solve it. It'll be great. But that's the trick. If you got some of it, this is the trick. You solve for this. So you can use like another ratio. And he'll give you a copy. What fraction of the volume do I have? Boom, multiply that by the charge, that's how much charge I have. Whoa!
Oh no.
So you did all the
volume.
I remember some class.
I know, yeah. So what is the what's my volume in close? You were very close. Yeah, what's the volume of pi little r cubed?
Yeah,
Just
it's a
little r
little
cubed.
involved, but that's the
Oh.
You went over. You did.
I was doing
You found the volume in between the two. So if you do 1 minus your answer, you'll get the right answer. Yeah. Or if you do q minus your answer. Yeah. How'd it go? Yeah, yours good. You lost enough time.
Oh, yeah.
Yeah, but otherwise, you're good.
Based on that. B enclosed.
You have the opposite. Wait, what's just do your
You're doing
yeah. Yeah, just yeah. You're all good. Yeah, that's classic.
Yeah.
Yeah, that's really so
So both of those on the right equal up, right?
Let's write it out.
EQ enclosed. How do you feel about multiplying B enclosed by both sides? And you get B enclosed over B total times Q total.
Okay. Okay, so yeah.
Is that not just doing basic algebra?
Cool. Alright, write it out.
Yes, I am. I will do that.
Oh yeah, how'd that go?
Oh, you're right.
I got
Yeah, sometimes I didn't know how to go All right, Tyler, you want to go ahead and reveal it?
Can I do a new slide, probably?
Yeah, if you want to.
How do I do that? Is it in home?
This button. Yeah.
New slide?
Yep. And you can copy if you want any of that, or you can redraw it.
Okay, how do I get rid of these things?
Just click it and delete.
Okay, gotcha. All right. So I'm going to draw our charge here. This is our little surface with Q as the charge, and we're looking for a Gaussian surface inside of it. We can say that the entire radius is big R, and this little radius here is little r. Hopefully that makes sense there. And we're going to use the fact that this is a uniform charge distribution, so that our rho is going to be the Q total over the total volume. But like was mentioned before, this is also the same as the enclosed charge over the enclosed volume. So we can solve for the charge enclosed here and say that it's the Q total. What do we got? Times the volume enclosed volume. And we can plug this back into our equation where it's E, the electric field times the area, equal to Q enclosed over epsilon naught. We know that the area of our Gaussian surface is going to be 4 pi little r squared equal to, and then we can plug this back in. I'll go back up here and show that this is, the total charge is just Q. Our enclosed volume is going to be 4/3 pi little r cubed over 4/3 pi big R cubed, and we'll see that this is just Q times little r cubed over big R cubed. We can plug that back in here and get Q times little r cubed over epsilon naught big R cubed. And then from this, we can just solve for the electric field. We'll have 1/4 pi little r squared times what we had before, Q r cubed, epsilon naught over r big R cubed. This r squared on the bottom is going to cancel. This is just going to be r on the top. So we'll have that E is equal to 1/4 pi epsilon naught Q r over big R cubed, or KQ little r over big R cubed.
There you go. So yeah, this gets down to, these are the two types of Gauss law problems. The last one we did, what if you're in a metal? We also did, what if you have all the charge? Now we've done, what if you have some of the charge? Make sure you can do all variations. But at the end of the day, it all boils down to, I mean, there's only a couple of things. Can you draw the Gaussian shape, the correct one? Do you know what you're doing with this E.dA business? Do you know how to find charge enclosed? How do you make sure you're good at this? Practice problems. There's already, if you're like, what the heck happened here? I don't know what's going on. Practice the problems in the problem set. They exist for a reason. There's one in the quiz that has this as well. If this is the first time you've done a problem like this, you should very likely do more of them. This stuff is not trivial. There is steps. There is a process. It takes practice. All right. So, great. That's everything to do with electric fields. Electric potential energy. It's the energy stored in a system. How do you store that energy? You bring some charge from far away. That's the work done. And so that's the integral for it. That is one of the integrals, and we're going to practice this integral, at least a variation of it. The energy in a system is determined by building the system one charge at a time. What's the energy required to bring one charge in? What's the energy required to bring a second charge in? What's the energy required to bring a third charge in? Add them all up. We'll practice one of those in just a second. Conservation of energy. Remember, your change in potential energy is going to equal your kinetic energy. Your change in kinetic energy. Things will move from high to low. So, oh, my picture. Oh, sad. It's all right. It's all right. Everything's fine. Oh, sad. This happens sometimes when I, all right, it's fine. It's fine. This happens when I like leave my thing open and it gets really angry that there's so much in it. Yeah, an error occurred because it hates everything. Please hold. It really won't want to save this, which means all my precious work is gone in some fashion. Yeah, whatever. Go away. Fine. Don't save. Goodbye. All right. Don't worry. I did all the work this morning, so it's still there. These things happen. Very sad for us. All right. Behold, all the answers. Oh, look. It's gone. All right. Find the energy. Okay, so this picture is a little different than the one online. Find the energy in this system. I got 3 charges, each with, this negative one is negative Q. This positive one is positive Q. Positive Q. They all have the same magnitude of charge. Find the energy in the system. Try it out. And then the second one is kind of really weird, and I actually need to kind of rephrase it for you all. I need to make a different one. So we're going to take this and move it here. Great. And then we're going to... Great. All right, so just try the first one for now, then I had to make the second one simpler to avoid complications. Remember the technique. Bring one charge in, then bring another charge in, then bring another charge in, then add them all up. The answer will not be 0. No. Sum all the energy. All right, and I'm going to give you all a hint. The change in energy is Q times the voltage. And the charges start infinitely far away where my voltage is 0. And then they move to where they're located where the voltage is no longer 0.
Plug it in for the second one for your control engine. Plug in what you put for the first one.
That's why I made it differently, because otherwise it's awful.
Yeah.
It's not awful, it's just you have to release everything and it gets
Right.
a little weird. All right, y'all. How much energy is required to bring in the first charge? So yeah, delta U1 plus delta U2 plus delta U3. Yeah, so how much energy is required to bring in the first one? 0. Why? There's nothing it's fighting against. It goes from 0 voltage to 0 voltage. So the energy required is 0. Great. Then I bring in my second one. And so what you all need to remember, this charge, this first one is making a voltage. What is the voltage that it makes at this point? What's the equation for the voltage due to a point charge? KQ over R. So it makes some voltage here. How much voltage does it make? And I'll kind of write it down here. Plus Q times negative KQ over R. Now this should hopefully look familiar. Remember the energy between two charges is just K, Q1, Q2 over R. That's where that comes from. So just to write this maybe a little differently, you get K, Q, negative Q, times positive Q, over what's my distance between them? A. Great, that's the energy to bring the second charge in. What about the third charge? Now that I bring that one in, how many charges does it see? 2. So you need the energy. So we get negative Q times positive Q over, what's the distance between those two? 2A plus K, Q, Q over A. So what's the total energy in my system? Algebra. It actually is quite nice. These cancel and boom, there's the answer. Why do they cancel? One's negative and one's positive. Does that always happen? No. That was just convenient. So the final answer to this is actually quite simple. It's just negative kq squared over 2a. Boom, that's the energy in the system. The key here, build the system. One charge at a time. That's what you got to do. All right. The problem on the bottom. Charge on the left is fixed in place. Charge on the right was released. What's the maximum speed it reaches? So this comes down to my energy initial plus my kinetic energy initial equals my energy final plus my kinetic energy final. All right. What energy do what's my starting potential energy in this system? How much energy is stored in it? What's the energy stored between two charges? Okay. I believe in you all. Q. Good. Yay! That's the energy I start with. What's the kinetic energy I start with? 0. Great. What's the energy I end with if it flies infinitely far away? 0. If I go infinitely far away, it doesn't have any energy anymore. They don't see each other anymore. What is my kinetic energy that I end with? All right, and then you just math. Rearrange this, solve easy. Like the rest of this is... So V equals 2 times KQ squared over A times M square root. On the test, some of the multiple choice will be purely in variables. And the free response, part A of every single problem is purely in variables. Hopefully I've convinced you that that's nicer, because you have to do everything in variables. And like plugging in numbers is an extra step. I'm saving you an extra step. Don't worry, I'm not going to make you all do any crazy like algebra or things like that. Just can you set up like done? Isn't that nice? You know what'd be worse? Having to plug that into a calculator. Because then I'd have to get out my calculator. This is it. It's done. So good. All right. So, this is great. We're finally getting close to the one that I really wanted to practice today, which is the voltage one. It's going to be a great time. So fun. Electric potential. So what causes this energy, this voltage, this height? Electric potential energy. Again, we can think of... Great. Okay, so I have some height here. How high is my hand above the floor? How many meters or so? Like 2 meters or so. Great. How much energy, how much potential energy do I have 2 meters above the ground? Yeah, is there anything here right now? Is there anything 2 meters above the ground? No. Do I have any energy stored there? No. How do I get energy there? I put some mass there. This is the same thing. Hey, how do you actually get some energy? Get some height and then put a charge there. It's the same idea. Just because you have a height doesn't mean you have energy. Just because you have voltage doesn't mean you have energy. Don't mix up the two. That was the purpose of that kind of statement. It's like height. You go from high to low. Anytime you all ever measured how high up something is, you always had a reference. If I ever said something's 2 meters high, there's some reference to some other location. Voltage is the same way. How do you make it? Charges, KQ over R. This integral is the one I want us to practice today. This integral is how we find the voltage. And how can we find it? By integrating the electric field over some distance. That's actually where this KQ over R came from. This KQ over R came from integrating the electric field due to a point charge. It didn't just come out of thin air. And then the last is just definition. Charges make this potential. Positive charges move from high potential to low. Negative charges move from low to high. Again, think of it like height, yada, yada. All right, so this is the problem I wanted to work on. This is the one we actually already started. Look, there's a bunch of work and it's going to be gone. My question to you all is I got a sphere. It's the same one we worked on before. And it says find the electric potential inside and outside of a uniformly charged sphere with a net charge of Q and a radius of R. So we're solving for the electric potential at two different places. Some distance r that's outside of it, and some other distance r that's in. So, let's call it in, let's call it out, whatever. What is the electric potential at these two places? Now, to solve this, it's not just a trivial KQ over R situation. You may look at one of them and be like, it's KQ over R. We've got to see why. One of the answers is KQ over R. The other one's not. And so it's important for us to understand the process here. How do we get this potential? How do we get this change of potential? If you all want to find the height of something, what do we tend to say we're measuring from? Like the ground, what do we set the ground at? What value? 0. Awesome. So when we're going to build this integral, and we're going to want to integrate from somewhere where the potential is 0 to somewhere where the potential is what we want. Where we actually want the potential, that random spot we picked. My question to you, and I actually kind of listed it there. Where is the potential going to be 0? Where can I find a potential that's 0? And I'll tell you on the test, I'll kind of give you these bounds just to make things a little bit more streamlined. Who has any guesses? Where is the potential 0 relative to this object? Ooh, we got some different answers. So we got the center. So these expressions are actually the answers. And I know it's kind of weird to use the answers. If I make little r 0, does that come out to 0? No. But let's look at this one. This one is the potential outside of it. And that should be some little r. That's actually a typo. When does this term turn to 0? What does r need to be such that this gets 0? Yeah, super big. What's the biggest number you can think of? Great. That's our bounds. Okay. So, what we're going to do here is I'm going to do the outer one. We're going to kind of talk through that one. And then I'm going to let you try the inner one, and I'll give you some hints for it. So if I want to find the delta voltage outside of it, I'm going to go from infinity to R. If I want to find the voltage at this point, I'm going to take my charge, put it somewhere where the voltage is 0, and then bring it to where I want to find it. Cool. Let's see if y'all remember. There's an electric field inside of this object, and there's an electric field outside of the object. When we're outside of it, you all just derived this. This is not hopefully something surprising. This was the equation that we came up with in a few slides ago. This is why we did that problem. We did Gauss's law to find these fields. I need to choose the right field. If I'm going to integrate from infinity to R, I need to choose the right field. If I'm way out here infinity, what's my field there? Is it the one inside the sphere or outside the sphere? Outside, great. What if I get closer? Am I inside or outside? Outside, great. What if I'm at this point where I'm wanting to find the potential? Am I inside or outside? So what do you think we're going to integrate over? Which one? The outside one. Now, there is something we got to be careful of. This field, which way does the field point? Outwards or inwards? If it's a positive charge. Great. Which way am I moving? What's the angle between those? 90. Not 90. Close. Remember, y'all, when we do this dot product, it's the cosine of the angle. Try it out. Try to do the integral, y'all. Get the voltage at this point. You got all the things. We're outside it the entire time. Just plug everything in. Try this outside part. The inside one's the fun one. You got to break the integral into 2 pieces. And then this is the last complicated thing we're doing in this rest of the PowerPoint. The rest is going to be pretty, capacitors and resistors are really straightforward. So we are, believe it or not, near the end. I know it's a lot, but that's because it's 5 weeks of stuff in one day. Because where do we start?
That's
What
how
level?
you're moving.
Yeah.
Right.
That's a good question. So we started far away. So basically, it's like saying how high up. I want to figure out how high up something is. I need to start with a reference. Once it can be used as a reference. So like, if I want to measure how high this is, if I set the reference to the ground, what will I set the height? So we're going to start someplace with voltage 0. So that's my issue where what voltage, that voltage minus 0 is our bottom of the voltage.
This one? Yeah. Yeah.
Because it's infinitely far away. It's not true of every person. It's true like if it's still a test, I'll start. Or I'll say find it between these two points. You won't have to worry so much about that. So I will say, an extra negative sign, but I'm not quite sure how.
I just did the one from the inside. Is this where you start with the surface and then you integrate from the surface to the inside point?
Yeah. You can take this. You can take that solution.
Okay.
Yep. Yeah, you build it into 2 pieces.
I actually don't know how to do the.
All right, so we get the integral from infinity to r of the electric field is kq over r squared dr. Hopefully you're like, this is a really easy integral because it is. I don't know. It's kq over little r with the negative sign. Great, we go from infinity to r. We start at infinity, we end at r. Now, I will say this does spin on a negative, which I kind of have to figure out, I have to think about a little bit more, because obviously our answer is positive, and it kind of sort of should be positive. So I have to think about that a little bit more, but we're basically there. Yeah, I canceled out our other negative, was the bummer.
So the answer should be positive?
The answer should be positive, so I have to think about this positive a bit more, and I'll, but don't worry about it too much about it. I'm not going to knock you on something that I have to think about more myself.
I think it might be because the lower bound is infinity.
I know, yeah, it's like, but it shouldn't be the upper bound because you start.
I don't know, but it could be the same as the negative flip of that. I feel like, but I could be wrong.
I don't know. So I'll think about it a bit more. But while I'm thinking about it, I want you all to do the second one. So here's the key to the second one. We're going to do the same integral. We're going to start with that same integral, delta v. But now we're inside of it. Why does this matter? We're still going to do our integration. But here's the problem. Is my field the same on the outside and the inside? No. Why does that matter? If I'm doing this integral, why does that matter? I start infinitely far away. My field in this region is one value, and when I'm inside, it's another value. An integral is the same thing as a summation. So what am I going to have to do if my electric field changes in 2 different locations? What am I going to have to do with that integral? I got to split it into 2 pieces. You all need to integrate when you're outside of it. And then you all need to integrate when you're inside of it. Now, the bounds are the interesting things that come out here. When I'm outside of it, where do I start? Where do I end? I end at capital R. When I'm inside of it, where do I start? Capital R. Where do I end? At little r. What am I doing? I'm taking my object from infinitely far away and bringing it in. That's what I'm doing here. So anywho, try this out. Plug in the things. You should be able to get the as weird as that expression or something that's, if once you simplify it, turns to that. All right, this is a bit more I'm not going to on the test have you where you have to split the integral into two pieces, but I do need you to know that you can integrate the electric field to get the voltage. I need you to know that you can do that. On the test as well, I'll give you all some hints about what the bounds should be. For example, maybe I'd say find the delta V between these 2 points. And if I wanted to make this energy instead of delta V, you just chuck a Q in front of it. If I want to say how much would the energy change if I moved a charge from here to here, just chuck a Q in front of this. If you're like, what is he talking about? Delta U is just negative Q integral of E dot dr. It's the same equation with a Q, which is equivalent to the work done. Yeah, try that second. Yes.
You're going forward from the outside.
So what you said?
That's why you're still getting that.
I know, but
Oh, right. Yeah, we would have used the, we're not going to put it. Would you be able to like plug it into that? Well, we said and then we're going to go all the way. I'd probably use that. I guess it's
Yeah. The field will still be outwards.
The one on the other side?
Because it's a positive.
Yeah.
If we could drive.
That becomes the big R there.
Yeah.
This one is
Right.
It's really
infinity on the bottom. It's the same like position of the big R.
Yeah, but I have to start an infinity.
It's the same thing though, mathematically. I think that's why, because like by definition the lower body has to be on the bottom. So,
Oh no.
like, writing it that way makes it good, but like it spits out a negative. I'm pretty sure.
Okay. You think that the negative? So you think it should just be?
Like you can leave it that way, it just spits out a negative because of the like you're going the opposite way.
We should end at the low point and start at the high point, is what you're saying.
Yeah.
Okay.
Like
So, all right. Tyler has an idea, and I think it's right. I think these bounds should be flipped, which is not intuitive per se, but it does come from when an object drops. Where do we start from? A high point or a low point? A high point, and we end at a low point. So that's kind of what we're doing here. We start at the high point and a low point. It's kind of weird. Don't worry about this on the test. That's my thing for you. You can set up this integral and solve it. Don't really worry about the positive, negative answer at the end. I'm not going to knock y'all on that because it's a little funky and there's some value in knowing it, but whatever. So whatever. On the test, though, again, I'll give you the bounds. I'll say where to start. I'll say where to end. Do the things. But anyway, that'll give us that positive. Mm-hmm. As weird as it all is. Yeah. No, I think because it comes from the definition of work.
Yeah.
Changes energy, and we tend to start with the high, go to the low.
I think they consider any integral improper too if the lower bound is bigger than the higher bound. Yeah. Like it just has to flip it and get the negative. Yeah. Pretty good. I've got a midterm tomorrow that I'm very nervous about. I always get sick before midterms. It's like a curse or something. I know. I was planning to start studying my grades on Sunday. That's when I got sick. Well, I feel decent. This is the first midterm, so I have like no idea what to expect, you know, which I always hate, but it's partial differential equations, so one of the hardest subjects in math. I feel like she'll be a little generous the first one. Fingers crossed.
When the first one sets the bar, and then you get lower.
All right, so there's more. I can't fit it all. So the integral that you all are solving in the second part is just that kq little r over big R cubed. What's the integral of that little r? It's just r squared over 2. You do need to evaluate that at the bounds from little r, or sorry, big R to little r. That's what I ran out of room for. Again, I'm not going to ask one that has this much involved. Why did I put this problem on here then? Why you're like, why did you give us one so terrible? I really like this problem for showing what you're doing. That you're starting somewhere infinitely far away. You're bringing it in to find the potential between 2 points. And if the field changes, you got to care about that. But again, I'm not going to give you one where the field changes on the test. So, we can just pull out this kq over 2r cubed. And then we just have little r squared minus big R squared. And if you end up simplifying it, it turned into the thing that we had. We're not going to bother with that, though. Can you do the integral of the electric field? That's my question to you all. Should be very straightforward. It's just this one we did do the integral because it's easy integrals, Calc 1 integrals, right? All right. For the sake of our brains, we're not going to, again, we're on capacitors now. This is going to go much smoother. Capacitors are really straightforward. What is capacitance? How much charge I can store on something. I did forget to put a little variable. Oh, I put it down here, but I'll put it up here as well. Capacitance is a geometric property that depends upon whether or not you have a dielectric. Oh, hey, but it does it. I need a little symbol kappa. Oh, hey. All right, whatever. Epsilon naught A over D. Yeah, I can go over to the formula shade here to just put it in here, and that'll save me some frustration. But I was trying to use my cool little macro. Yay, there it is. All right. Kappa, epsilon naught A over D. Bigger area, more charge. Bigger distance, less charge. Something very important about capacitors. What is the electric field inside a capacitor? I didn't put it here. Does anyone remember it off the top of their head? Sigma over epsilon naught. The only equation that you all should have, like, I didn't put on the formula sheet, but it could be useful on your note card. The equation for the electric field due to one infinite plane is sigma over 2 epsilon naught. What is a capacitor? It's just 2 of them together. Double it. Why is this special? It only depends upon charge and area. This does not depend upon the distance at all, which is something that's very important and I've mentioned several times. Energy stored in a capacitor, we derived that by doing an integral, but you don't need to be able to do that, but you do need to know the equation. And you also need to remember what stays constant on a capacitor. If you're connected to a battery, voltage is going to be constant, no matter what you do to the capacitor. If removed from a circuit, charge stays constant, unless you discharge the capacitor. If you don't destroy the capacitor by changing any qualities about it, then the capacitance stays the same. If I don't change its area, distance, or dielectric, boom, it stays the same. Dielectrics are helpful. They increase our capacitance and the energy stored. Well, in this case, it looks like less energy, but. All right, so. Last thing you all basically need to know from capacitors is how to combine them. We spent a bunch of time on that. Anytime you all spend on this will pay dividends for future content, because the first thing we're going to cover after this test is resistors in series and parallel. So Capacitors in series, they add all with the inverses. Capacitors in parallel, they just add. Charge is constant in series, voltage is constant in parallel. If I had a bunch of circuits together and I wanted to find the charge and voltage, you'd combine them all and then go backwards. And we did an example of that previously. So, practice adding these capacitors together. They all have the same C. This one's got C, this one's got C, this one's got C. Find the net capacitance. Capacitors will not be a free response question. Now, all the rest of this is like multiple choice because it's all just kind of basic. These ones are like the most complicated, but I don't want to put one of those in the free response. You'll get plenty of chance for that with resistors. So it's all in variables, which are like, it's great. No calculator. There's the final answer whenever you get there. First, you got to identify if any are purely in series or purely in parallel. Series is always the easier one to spot. So start there. None are in series, then look for the parallel ones. Yeah, great strategy I just saw someone do, which I appreciate, is color your voltages. That'll help you make sure if you think some are in parallel, that'll let you confirm it. They start and end at the same voltage.
Oh, I have a question.
Yeah. You just don't care about the dot product.
Maybe it's just one of those physical interpretation things where they just make it right after. Is it, oh, I shouldn't be there. Should I say?
Because even here they say the work necessary to bring a charge from an infinite distance to some distance. Okay.
Yes. But make it seem like a lower bound infinity.
But then they say, make R be infinity.
I want to read up on that now.
But why?
That's interesting.
All right, so just to color code things. So here's my voltage is 5 volts. Then on the green is who knows what. And then on the blue is 0. So what I hope y'all realize is even though these look like they're in parallel, they're in series. Why are they in series? They're one after the other. And you can also see they don't have the same colors on both sides of them. How would we know they're in parallel? They should have the same colors on both sides of them, the same voltage drop. They don't. Just because they look like they're parallel doesn't mean they are. Parallel doesn't mean geometrically parallel. Parallel means same voltage across some series, means one after the other. These are one after the other. I can easily go from this one to the other one, no problem. Nothing's in between, easy. So anywho, combine these. These are in series. So these are in series. How do I combine capacitors in series? They're really fun. 1 over C equals 1 over C net. So that turns into C net is 1 over C plus 1 over C, which is 1 over 2 over C, which is C over 2. Fun fact, whenever you add inverses, you should always end with a smaller number. Whenever you do this whole inverse operation, your final result will always be smaller than the smallest element in it. That's just how the math works. Great. Then we redraw the circuit. So now I got a capacitor up top. I've got my voltage source. I've got one up top, and I've got one on the bottom. Capacitor, capacitor. Those are in parallel. How am I going to add those together? You just add them. This one's C over 2. This one's C. So C net equals C plus C over 2 equals 3C over 2. Great. Awesome. What's the charge and voltage on each one? So just to kind of blitz. Oh, my pictures are hideous here. So I'm going to draw this much nicer. The way you always kind of want to do these is you draw every single step in the process. So I call this one C, Q, and I leave myself ideally space to write C, Q, and V over each of them. If I know I'm going to have to do this. C, Q, V, C, whatever. C, Q, V, C, Q, V equals C, C. C. All right, then I turn this into the, combine the ones on the bottom. That one is C. That one is C over 2, Q, V. Fun fact, we didn't actually need to combine these. What's the voltage drop across these, even without combining them? Yeah, it's just 5. So you actually don't even need to combine them to figure this out. And then you can do the whole C equals Q over V. Q equals C times V. So that equals 5C over 2. That one's also 5C over 2. Go backwards. This one's also 5. You know, it's the same one. 5 volts. 5C over 2. 5C over 2. And the voltage equals Q over C. So that equals 5 halves. 5 halves plus 5 halves equals 5. No works. But anyway, if I did want to turn this into one capacitor, that's that 3C over 2. If you did want to find this one, which it turns out we didn't need to, but it's not too bad. Yeah, it's right here. Did I not write that? Oh, just 5C? For this one up here? Let's see. That's a great question. Did I put a 2 there for no reason? Yeah, I did put a 2 there for no reason. Yeah. You're right. 5C. I'm double checking myself. Yep. Great. All right. The bottom's still good. Okay. Great. There's capacitors. Make sure you can go through all this, do capacitor things. Yay. Last thing is just resistors. We're not even really, I don't think I even have a practice problem for this. Oh, I do. But whatever. These are the things you need to know about resistors. You do not need to know about power. You need to know that current is defined as the amount of flow of charge per second. Resistance is based on the materials and the geometric qualities of that object. It depends upon temperature. And V equals IR. These are going to be very straightforward. If I give you a problem on a test about this, it's literally just, hey, length is this. Radius is this. What's the resistance kind of thing? Like, these are very plug and chug problems. What am I solving for? Find the equation for it. Look, if I ask for resistance, there's literally only 2 equations on the entire formula sheet that's got an R in it. You're probably going to use one of those. One of those 2. What you have is what you're going to use. If you have voltage and current, use that one. If you have length and area, resistivity, use that one. They're very straightforward. No resistance circuits. I haven't even showed you what a resistor looks like in a circuit yet. So yeah, you're spared that. That'll be a test 2 thing. All right. So great. Try this out. It's the last one. If you can do this, can you do the equations? What am I solving for? What do I have? Plug stuff in. Just, hey, can you use the equations? And that's it. This will be the end. We got through 5 weeks of stuff. And yes, it takes a while because it's 5 weeks of stuff. But good hustle, everyone. Oh yeah, it's a good question. It's a circular wire. I will never give you any other wire. Our wires will always be circular cross section. I have never seen a wire that's not circular cross section, which is why they can technically exist, but they're hard to make. Yeah, and that comes to the engineering wise of it. Circles are easier to extrude than a square thing. Maybe in a transistor or stuff like that, though. Those are kind of squarish. But then you have other problems. You do have sheets, but are they running current through sheets? Maybe.
Like yeah.
You probably show geometry as a flat rectangular thing. It's like a whole instance, I guess, but that's. All right, so let's, what am I solving for? L. There is literally only one look, we got some mention of resistivity. There's only one equation on the formula sheet with an L in it. It's R equals rho L over A. So I look at this. Oh, I've got resistivity, area. Oh, that equals pi r squared. Great. Sure would be nice to know R, though. Oh, V equals IR. So R equals V over I, and then you just move things around. So rho L over pi r squared equals 3v over I. Rearrange this for L. You get 3v pi r squared over rho I. And there you go. All right, y'all. So, takeaways. Make sure you can do Gauss's law. Make sure you all can integrate electric field. There's a couple example problems other than the ones we did. That can be good reminders for that. I also had one on the last problems, on the last quiz, had a problem that said find the delta potential, and I gave you the electric field, and it gave you some points, and you had to do integration. So there's one of those, and yeah, otherwise, you know, make sure, rule of thumb, if you look at the formula sheet, you should know how to use every formula that we've covered. That's a great way to make sure you're prepared. Just go through and be like, yep, know how to use this, know how to use this, know how to use this, know how to use this. If you don't, you should probably find a problem that uses it. That's a great way to study for like any of your all's physics or engineering courses. If there's a formula sheet. All right, y'all. Best of luck. I'll see you Thursday. It's going to be a grand time. You'll get the full 2 hours and 50 minutes in the exam. So much fun together.